session, you will be able to drill through hole, bore a hole to an accuracy of plus or minus 0.2 mm with a tool. Perform step boring. Performing internal recess. Measure the bore and recessing with the help of vernier caliper and inside caliper. The tools required to perform this exercise are outside caliper, inside caliper, steel rule, chuck key, facing tool, drill bits of various size, vernier caliper, radius gauge, recessing tool, boring bar, R2 and R3 tool. Boring is the process of enlarging the diameter of a pre-drilled hole using a boring tool. Recessing is the process of cutting an angular channel inside the bored hole. Let us now learn the sequence to drill a hole and bore it to the required size. Check the dimensions of the workpiece using outside calipers and steel rule. Mount the job on a 3-jaw chuck using a chuck key such that 45 mm is outside the chuck. Perform facing operation to the one end of the workpiece. Perform turning operation for the maximum possible length to reduce the diameter to 45 mm. After making a center drill, hold a pilot drill of 10 mm along with the chuck in the tailstock. Move the tailstock to a convenient position for drilling and lock the tailstock on the bed. Run the lathe and advance the drill so that it does the drilling operation on the job held in the chuck to obtain a through hole. Use a coolant while drilling and advance the drill slowly. Enlarge the hole to 14 mm by drilling. Mount the boring tool on the tool post. Set the cutting edge of the cutting tool just slightly above the center line, since there is a tendency for the tool to spring downwards when cutting. Start the machine and turn the cross slide handle anti-clockwise until the cutting tool touches the inside surface of the hole. Take a light trial cut about 0.2 mm deep and about 8 mm long at the right hand end of the work. Stop the machine and measure the diameter using a vernier caliper. Set the cutting tool for the required depth to get the finished bore size. Use the cross-slide graduated collar. Finish the boring operation to the required diameter of 15 mm and measure with a vernier caliper. Reverse and refix the job. Perform facing operation on the other end to obtain a total length of 45 mm. Perform turning operation to obtain 45 mm diameter throughout the length. Let us now learn the sequence to perform step boring and internal recessing. Mount the boring tool on the tool post. Use the largest diameter boring tool, which can be accommodated in the drilled hole. Perform boring operation to a length of 33 mm from the faced end to obtain 28 mm diameter hole. Mount R2 boring bar on the tool post. Calculate the distance from the face to the edge of the groove farthest from the end face. 29 plus 4, which is equal to 33 mm. Touch the edge tool to the face of the workpiece using the top slide handle and set the compound slide graduated collar to 0. Turn the cross slide handle so that the front of the tool just clears the wall of the bore. Turn the top slide handle to position the tool at the calculated distance into the bore. Turn the cross slide handle wheel in an anti-clockwise direction to advance the tool and touch the bore and note the cross-feed graduated collar reading. Rotate the cross-slide handle wheel in the same direction to make the tool remove the metal from the bore to form a 4 mm wide, 35 mm diameter and 2 mm radius recess. Retract the tool by moving the saddle towards the tailstock. With a R3 radius tool, turn one edge of the workpiece as per sketch. Deburr all the sharp edges. Check the radius with the radius gauge and other dimensions using calipers. Safety precautions. Select and set proper spindle speed as per size and operation. Set the tools to the correct center height. Use pilot drill while drilling more than 20 mm drill size. Feed the drill slowly while drilling. Use a coolant while drilling. Grip the boring tools as short as possible to reduce shatter. To recap, we have learned to drill through hole. Bore a hole to an accuracy of plus or minus 0.2 mm with a tool. Perform step boring. Performing internal recess. Measure the bore and recessing with the help of vernier caliper and inside caliper.
So that's all about boring practice plane, counter and step, internal recessing. See you in the next session. and welcome to this session on reaming in lathe using solid and adjustable reamer. Let us begin with the session.
Let us now look at the objectives of this session. At the end of the session, you will be able to drill a hole to size, leaving allowance for reaming. Ream through hole with a hand reamer. Check the reamed hole by using a plug gauge. Enlarge the reamed hole by diameter 0.1 mm using adjustable reamer. The tools required to perform this exercise are outside calipers, steel rule, chuck key, facing tool, turning tool, center drill with chuck, drill bits, chamfering tool, reamer, tap wrench, plug gauge, adjustable reamer. Reaming is a machining operation in which a rotary tool takes a light cut to improve the accuracy of a round hole and to reduce the roughness of the hole surface. A reamer is a multi-point cutting tool used for finishing previously drilled hole to accurate sizes. Reamers are classified as hand reamers and machine reamers. Hand reaming is done manually, for which great skill is needed. Machine reamers are fitted on spindles of machine tools and rotated for reaming. To determine the size of reamer, drill size is equal to reamer size minus undersize plus oversize. Reamer size is the required finished hole size. Example, drill size equal to 16 mm minus 0.2 mm plus 0.05 mm, which is equal to drill size equal to 15.75 mm. Let us now learn the sequence for reaming operation. Check the size of the workpiece using vernier caliper. Hold the job in a 3-jaw chuck such that about 25 mm is outside the chuck. Perform facing operation on one end of the workpiece. Perform turning operation to obtain diameter of 30 mm to the maximum length possible. Reverse the job and refix it. Perform facing operation on the other end of the workpiece so as to maintain a length of 30 mm. Perform turning operation to obtain diameter of 30 mm to the remaining length. Hold the center drill in a drill chuck mounted onto the tailstock barrel and center drill the work. Drill a 10 mm pilot hole. Drill through hole in the job with diameter 15.75 mm drill bit. Chamfer the drilled hole 1 into 45 degrees. Fix up the tap wrench to the square end of the diameter 16H7 hand reamer. The tap wrench must be short enough to clear the lathe bed. Move the tailstock back so that there is sufficient space for the reamer between the dead center and the workpiece. Place the reamer into the pre-drilled hole slightly with the shank supported by the tailstock dead center. Ream the hole by using sufficient coolant. Give uniform hand feed while reaming. Check the hole with a go and no-go plug gauge. Enlarge the reamed hole using adjustable reamer to a size of diameter 16.1 mm. Let's learn the precautions to be taken while reaming. Do not turn in the reverse direction. It will scratch the reamed hole. Remove the reamer occasionally by turning it clockwise to clear off the chips from the flutes. Never use a hand reamer under power. If the plug does not go throughout the bore, it indicates that the bore is tapered. If the hole is within limit, the gauge will enter easily. An entry of a no-go gauge into a hole beyond the chamfered length indicates an oversized hole, well-mouthed or tapered hole. To recap, we have learned to drill a hole to size, leaving allowance for reaming. Ream through hole with a hand reamer. Check the reamed hole by using a plug gauge. Enlarge the reamed hole by diameter 0.1 mm using adjustable reamer.
So that's all about reaming in lathe using solid and adjustable reamer. See you in the next session. Hello and welcome to this session on make bore by trepanning. Let us begin with the session.
Let us now look at the objectives of this session. At the end of this session, you will be able to set the square plate on a 4-jaw chuck. To cut the 70 mm diameter with the help of trepanning tool. Measure the diameter with the help of steel rule. The tools required for this exercise are steel rule, chuck key, drill chuck, drill bit, trepanning tool, box spanner. Trepanning is the operation of producing a hole by removing metal along the circumference of a hollow cutting tool. Trepanning is performed by using a hollow cutting tool. Trepanning is a technique used for drilling larger diameter holes where machine power is limited, where fewer chips are removed and much of the material of the hole can be removed as it is. Trepanning is performed on very thin workpieces at a very low spindle speed. It can be performed simultaneously on properly aligned multiple sheets so that when they are separated, the hole produced in each sheet will be of uniform size and will be located uniformly from the edge. Let us now learn the sequence to make the bore by trepanning. Check the dimensions of the workpiece using steel rule. Hold the square plate on 4-jaw chuck. Set the job on the 4 jaws by adjusting equal distance of reference concentric circle line. Mount the drill chuck to tailstock spindle. Hold the diameter 10 mm drill on the drill chuck. Perform drilling operation to obtain a pilot hole of 10 mm through the entire length. Fix the guide pin to the trepanning tool. Set the trepanning tool to drill chuck of tailstock to make a bore of 70 mm dia. Clamp the tool holder in correct position and center height. Select and set correct RPM. Locate the guide pin to the guide hole of the job. Move the tailstock, giving a gradual depth of cut. Make a bore of diameter 70 mm through the 6 mm depth. Stop the machine and remove inner piece. Trepanning tool is withdrawn carefully. Check the dimensions. To recap, we have learned to set the square plate on a 4-jaw chuck. To cut the 70 mm diameter with the help of trepanning tool. Measure the diameter with the help of steel rule.
So that's all about making bore by trepanning. See you in the next session.
In this session, we will learn about balancing, mounting and dressing of grinding wheel pedestal. At the end of this session, you will be able to know the grinding wheel, determine balancing of grinding wheel, adjust the clearance between tool rest and grinding wheel, and learn the use of wheel dresser and types.
Satisfactory results can be obtained only by having the right type of abrasive wheel rotating at the correct speed for the kind of work that is to be ground. Abrasive wheels are made from manufactured abrasive grains held together by a suitable binding material called the bond. The two abrasives used in the manufacture of grinding wheels are aluminum oxide and silicon carbide. The aluminum oxide grinding wheels are suitable for grinding high tensile, tough materials and all types of steels. The silicon carbide grinding wheels are used to grind hard materials such as stone or ceramics, non-ferrous metals and other non-ferrous materials. The type of the abrasive is clearly marked on an abrasive wheel by the manufacturer. Abrasive particles in a grinding wheel are held together by a material called the bond. The bond may be vitrified, silicate, and organic. Vitrified bonds produce strong, rigid grinding wheels that are not affected by water, acid, or normal temperature changes. Most of the abrasive wheels are produced with vitrified bonds. A silicate bond produces a wheel with a milder cutting action than a vitrified bonded wheel. Large diameter wheels have a silicate bond. The organic bonds may be made of resinoid, bakelite, rubber, and shellac. The organic bonded wheels have a safe higher operating speed. They are better able to withstand rough usage. They are used on portable grinders and for rough foundry work. Thin cut-off wheels are made with an organic bond. It is the amount or grade of bond that determines the hardness or softness of an abrasive wheel. The cutting action of a grinding wheel depends to a large extent on the grade of bond of the wheel. The principle is that the individual abrasive grains are small cutting tools. The bond must be such that it must hold the grinding particles together when they are sharp and must release them when they become blunt so that new sharp grains take their place to continue the cutting. This continuous process is known as the cutting action of the wheel. Use soft, light bond wheels to grind hard materials and hard, firm bond wheels to grind soft materials. Now let us perform few tasks to test your understanding. To do this, you need a pedestal grinding machine, clamps, mandrel, protection guard, diamond dresser and holder, and spanner set. The first task is to balance a grinding wheel. The job sequence is as follows. Check grinding wheel for cracks by light tapping. Unclamp balance weight of grinding wheel. Prepare the balancing unit. Clean the bore of the unit and the balancing mandrel. Mount the wheel assembly on the mandrel. Fix the protection guard. Place the wheel to be balanced on the top of the protection guards and lower gently on to the balancing stand. Rotate the grinding wheel so that it can rotate by itself due to its momentum and rests at a heavy point. Mark the lowest point on the wheel. Turn diametrically opposite point, add balancing weight, moving to lighter side. Repeat the above until the assembly remains static in any position. To assemble a grinding wheel, the job sequence is as follows. Clean the machine and remove any loose metal or abrasive particles. Loosen the work rest clamp and remove the rest. Remove the outer plate of the wheel guard. Check the nut direction before loosening. Remove the nut and the outer flange. Remove any paper, washer that has adhered to the flange. Clean the flange, spindle, thread and inside the guard. Push the wheel carefully against the driving flange and place the outer flange in position. Screw up the clamping nut by hand firmly enough to hold the wheel in position. Turn this.
Hi trainees, welcome. In this session, we will be learning about fitting of male and female threaded components. At the end of this session, you will be able to know the buttress thread, explain the male and female threaded fittings, describe the important elements in tool grinding and assemble buttress threaded component.
Let us get started by knowing about the buttress thread. In buttress thread, one flank is perpendicular to the axis of the thread and the other flank is at 45 degrees. These threads are used on the parts where pressure acts at one flank of the thread during transmission. The diagram shows the various elements of a buttress thread. These threads are used in power press, carpentry vices, gun breeches, ratchets, etc. This is a modified form of the buttress thread. This diagram shows the various elements of the buttress thread. The bearing flank is inclined by 7 degrees as per Bureau of Indian Standards BIS, and the other flank has a 45 degrees inclination. In general, the male threads or male fittings are the helical grooves found on the outside diameter parallel to axis, for example, bolt. The female threads or female fittings are the helical grooves found on the inside diameter parallel to axis, for example, nut. Let us know more about the internal threading. Buttress internal thread turning is more demanding than external thread turning due to high need of efficient chip evacuation. Chip evacuation, especially in blind holes, is helped by using left-hand tools for right-hand threads and vice versa, pull threading. However, this also creates higher risk of insert movement. Boring bar section has a strong influence on the quality of internal threading. 3 types of bars can be used for internal threading. There are steel boring bars with maximum 2 to 3 into bore diameter overhang, steel dampened boring bars with maximum 5 into bore diameter overhang, and carbide boring bars with maximum 5 to 7 into bore diameter overhang. External threading can be produced in number of ways. The spindle can rotate clockwise or anti-clockwise with the tool fed towards or away from the chuck. The thread turning tool can be used in normal or upside down position. The latter helps to remove chips. Important elements in tool grinding are the provision of flank clearance and radial clearance for precise and accurate threading. Let us have a detailed look at the flank clearance. Flank clearance is the cutting edge clearance between the sides of the insert and thread flank. Here is a diagram indicating the side clearance and flank clearance. Buttress thread is designed to handle externally high axial thread in one direction. The lead bearing thread face perpendicular to screw axis. Buttress thread often used in the construction of artillery, particularly with screw type breech block. They are also used in vices in the form of pipe thread in oil field tubing. This thread gives a tight hydraulic seal. To give adequate radial clearance, inserts are tilted in the tool holder by 10 degrees or 15 degrees. It is important to use internal inserts with internal tool holders and vice versa to ensure that the correct thread form is achieved. Let us now see how to assemble buttress threaded component. For this, you need male thread, female thread, measuring tool, bench vise and packing piece. The job sequence is as follows. Clean the external and internal buttress threaded job. Check the thread dimension, pitch and thread profile. Hold the male threaded job in vertical position using a bench vise and packing piece. Tighten to match the male threaded component by rotating in clockwise direction to the female buttress threaded component.
We have reached the end of this session on fitting of male and female threaded components. By now, you should be able to know the buttress thread, explain the male and female threaded fittings, describe the important elements in tool grinding and assemble buttress threaded component. In this session, we will be learning how to make a test mandrel L is equal to 200 mm and counter bore at the end. At the end of this session, you will be able to know the lathe mandrel, list the types and uses of mandrels, explain the boring and counter sinking process, set up the job in between centers using straight tail carrier and turn the job to the required accuracy.
Let us get started by knowing about the lathe mandrels. These are the devices used to hold the job for machining on lathes. They are mainly used for machining outside diameters with reference to bores which have been duly finished by either reaming or boring on a lathe. The standard solid mandrel is generally made of tool steel, which has been hardened and ground to a specific size and is ground with a taper of 1:2000. It is pressed or driven into a bored or reamed hole in a workpiece so that it can be mounted on a lathe. The ends of the mandrel are machined smaller than the body and are provided with a flat for the clamping screw of the lathe carrier. This preserves accuracy and prevents damage to the mandrel when the lathe carrier is clamped on. The centers made in these mandrels are B-type, that is, protected centers. In such centers, the working portion is deep and does not get damaged while handling. Now, let us have a look at the types of mandrels. There are 6 types of mandrels. They are expansion mandrels. Expanding mandrels on a lathe are a type of mandrel that grip the interior diameter of a workpiece. The 2 most common types of expansion mandrels are split bushing mandrel and adjustable strip mandrel. Gang mandrel consists of a parallel body with a flange at one end and a threaded portion at the other end. A gang mandrel is especially useful when machining operations must be performed on a number of thin pieces which might easily be distorted if held by any other method. Stepped mandrel is used to save time in holding various board works. Screw or threaded mandrel is used when it is necessary to hold any machine workpieces having a threaded hole. Taper shank mandrels are generally used to hold small workpieces. The 2 common types of taper shank mandrels are expansion stud mandrel and threaded stud mandrel. And cone mandrel, where a job of large bore can be held between the 2 tapers and tightly secured by means of nut, washer and spacing collars. Now let us see how to test the true running of a lathe spindle with a test mandrel. Locate the taper shank of the test mandrel in the spindle taper. Hold a dial gauge stationary in the carriage, its plunger contacting the mandrel near its free end, and set it to 0 position. Rest the dial gauge plunger at right angles radially to the surface to be tested. Rotate the spindle along with the mandrel slowly by hand. Observe and note the reading of the dial gauge. Move the dial gauge near the spindle nose. Rotate the spindle along with the mandrel slowly by hand and note the reading. Take readings of the dial gauge while the spindle is slowly rotated. Verify the deflection of the dial reading and compare the value with the test chart. Adjustment of the spirit level with the plane surface. Boring is the process of enlarging and truing an existing drilled or core hole with a single point cutting tool. Boring a hole is necessary to enlarge a drilled hole larger than the drill size, as drills are available in standard sizes only. To obtain concentricity of the hole. To maintain accuracy of the hole. To obtain better surface finish. To remove the error formed by drilling and to facilitate the reaming operation. Boring is an internal operation performed on the drilled or cored holes. The cutting edge of a boring tool is ground similar to the left-hand plane turning tool, but the operation being performed is from right to left. Countersinking is an operation of beveling the end of a drilled hole. The tool used is called a countersink. Countersinking is carried out for the following purposes: to provide a recess for the head of a countersink screw so that it is flush with the surface after fixing. The commonly used countersinks have multiple cutting edges and are available in taper shank and straight shank. For precision countersinking needed for machine tool assembling and after machining process, countersinks with pilots are used. Let us see how to set up the job in between centers using straight tail carrier and turn the job to the required accuracy. To do this, you need a raw material, independent chuck, cutting tool, straight tail carrier, measuring tools, drill chuck and drill bits, grease and spanner set. The job sequence is as follows. Check the raw material size. Hold it in the independent chuck and true it with the surface gauge. Set the facing tool and face one end. Center drill the job and counter bore pipe 20 mm to a 5 mm depth and center drill the job again as per drawing. Reverse and true it an independent chuck and face the job, maintain total length 200 mm and center drill the job. Counter bore pipe 20 mm to 5 mm depth and recenter drill the job. Dismantle the chuck from the lathe spindle and fix the driving plate on the spindle. Mount the live center and dead center. Check the lathe alignment of between two centers. Hold the job in between centers with the help of a straight tail carrier. Use grease on the center before fixing. Turn the job with an in-feed of 1 mm to its max length. Check the diameter at both ends to ensure cylindricity of the job. If necessary, realign the job. Turn the component again, going another 1 mm feed second time, reducing to pi 41 mm. Finish turn pi 40 mm to its maximum length. Chamfer 2 by 45 degrees. Reverse and hold the job in between center. Turn pi 40 mm to the remaining length of the job. Chamfer 2 by 45 degrees. Check the dimension as per drawing.
We have reached the end of this session on Make a Test Mandrel. L is equal to 200 mm and counter bore at the end. By now, you should be able to know the lathe mandrel, list the types and uses of mandrels, explain the boring and countersinking process, set up the job in between centers using straight tail carrier and turn the job to the required accuracy. In this session, we will be learning how to make a job using different lathe accessories, namely driving plate, steady rest, dog carrier and different centers. At the end of this session, you will be able to know the lathe accessories, set the job in between centers using driving plate and set the steady rest to support lengthy job.
Let us get started by learning about the lathe accessories. The lathe accessories are machined, independent units supplied with the lathe. The accessories are essential for the full utilization of the lathe. The accessories can be grouped into work holding accessories and work supporting accessories. Let us have a detailed look at the work holding accessories. The work can be directly mounted on these accessories and held. The accessories are 4-jaw independent chuck, 3-jaw self-centering chuck, face plates, and lathe mandrels. Now let us have a look at the work supporting accessories. These accessories do not hold the work themselves. They support the work. The work supporting accessories are catch plate, designed with a U-slot and an elliptical slot to accommodate the bent tail of the lathe carrier. Driving plate, designed with a projected pin which locates the straight tail of the lathe carrier. Lathe centers, lathe or dog carriers, lathe fixed steady, and lathe traveling steady. A steady rest is a lathe accessory used to give extra support for a long slender workpiece in addition to the center support during turning. The most common types of steady rest are fixed steady rest and followed steady rest, also known as traveling steady. A fixed steady rest is fixed to the lathe bed and it is stationary. It gives support at one fixed place only. It consists of a frame containing 3 adjustable pads. A follower steady is fixed to the saddle of the lathe. As it follows the tool, it gives support where cutting actually takes place. In the follower steady, the support is continuous to the entire length of cutting. The follower steady rest usually has 2 pads. One pad is located opposite to the cutting tool and the other pad bears the top of the workpiece to prevent it from springing up. If the job shape is not round or where we cannot turn a true cylindrical surface on the job, it is not possible to support the job by a fixed steady rest. For those types of jobs, a device called cat head is fixed on the workpiece. The cat head is a type of bush. Its external surface is round. The middle portion is cylindrical and free to rotate. The 2 ends have the adjusting screws for holding and centering the work. After centering the work, the fixed steady is positioned and pads are adjusted to hold the cat head's center portion. When the lathe is running, the work revolves along with the ends of the cat head, whereas the center portion is stationary. Here is another type of cat head, which is a single piece, and it rotates along with the job. The work is clamped firmly in the lathe carrier. It consists of a cast iron or forged steel body and a clamping screw. It is designed with a straight or bent tail. It is available in a set of 10, capable of accommodating work of a wide range of diameters. The tails of the carriers are meant to locate and drive the workpiece for turning. To protect the finished surface from damages, a soft metal packing piece is used under the clamping screw. The purpose of a lathe carrier or lathe dog is mainly to hold the work and provide rotation by transferring the power from the spindle using special attachment. It is used to drive the work during turning between centers. It is also used for taper turning and threading. There are 4 types of lathe carriers. Straight tail carrier locates against the driving pin of the driving plate and provides a positive drive for the workpiece. Bent tail carrier engages into a U-slot of the catch plate and drives the workpiece. Clamp type carrier is designed with a clamping plate and adjustable screws. It holds a wide range of diameters of work because it is provided with a V-groove, adjustable bolts and nuts. And safety clamp type carrier is designed with safety top and bottom clamping plates. These plates provide a positive grip of the work during turning. Lathe center is used to support a lengthy work to carry out lathe operations. When a work is held in a chuck, the center is assembled to the tailstock and it supports the overhanging end of the work. The work is to be provided with a center drilled hole on the face of the overhanging end. When the job is held in between centers to carry out the operation, it functions together with a driving plate and a suitable lathe carrier. The center, which is accommodated in the main spindle sleeve, is known as a dead center, and the center fixed in the tailstock spindle is known as a live center. In construction, both centers are identical, made as one unit that consists of a conical point of 60 degrees included angle, a body provided with a Morse taper shank and a tang. The dead center is made of high carbon steel, hardened and ground, whereas the live center need not have its conical tip hardened as it revolves with the work. A good lubricant should be used for the dead center. Let us have a look at the most widely used types of lathe centers, their illustrations and their specific uses. They are ordinary center common type, half center, tipped center, ball center, pipe center, revolving center, insert type center, self-driving live center, female center, and swivel V center. A microset adjustable center fitted into the tailstock spindle provides a fast and accurate method of aligning lathe centers. Some of these centers contain an eccentric, others contain a dovetail slide which permits slight adjustment of the center itself to correct alignment. Now let us see how to set the job in between centers using driving plate and set the steady rest to support lengthy job. To do this, you need the following raw material: driving plate, cat head, lathe or dog carrier, cutting tools, measuring tools, spanner set, and grease. The job sequence is as follows. Check the raw material size. Hold the job outside face and center drill on face. Reverse the job, repeat the same by correcting total length. Dismantle the check from lane spindle and fix driving plate on spindle. Mount live center and dead center. Attach a follower steady on saddle. Hold the work in between centers by using a suitable carrier. Support the job by follower steady. Apply grease on the touching pads of steady. Check the alignment between two centers by giving trial cut. Turn a 40 mm in maximum possible length. Chamfer the end to by 45 degrees. Reverse the job. Turn 40 mm in remaining length. Chamfer the end to by 45 degrees. Reverse the job. Turn 40 mm in remaining length. Chamfer the end to by 45 degrees. Check the dimensions as per drawing.
We have reached the end of this session on make a job using different lathe accessories, namely driving plate, steady rest, dog carrier, and different centers. By now, you should be able to know the lathe accessories, set the job in between centers using driving plate, and set the steady rest to support lengthy job. In this session, we will learn how to make the carpentry vise lead screw. At the end of this session, you will be able to know the carpenter vise, explain the buttress form of thread, describe the screw thread, turn the component as per drawing, and make buttress thread on the component.
Vices are used for holding workpieces. They are available in different types. The vise used for bench work is the bench vise or called engineer's vise. A bench vise is made of cast iron or cast steel and it is used to hold work for filing, sawing, threading and other hand operations. A carpenter vise is an important tool in carpentry and is designed to hold clamped wood without damaging the surface. Wood often needs to be clamped when completing tasks like sawing, drilling or carpentry. There are several varieties of vices available in the market. The following are the parts of a vise: fixed jaw, movable jaw, hard jaws, spindle, handle, box nut, and spring are the parts of a file. The box nut and the spring are the internal parts. To hold a finished work, use soft jaws or vise clamps made of aluminium over the regular jaws to protect the work surface from damage. clamps are mostly used in pairs for gluing up operations. It provides the required pressure to hold joints together. Basically, clamps are of two types: plain rectangular bar type and T-bar type. The clamps are mainly crafted out of mild steel and is usually rectangular in section. There are other types of clamps available, namely rack clamp, screw clamp, light duty pallet clamp, adjustable bar clamp, G or C clamp, and double bar clamp that are useful for holding different sizes and shapes of wooden jobs. The profiles for external and internal threads with clearance on the non-load bearing flank on the minor diameter but with no clearance between the load bearing flanks or on the major diameter nominal size is indicated in the diagram. The profile for external and internal threads with clearances on the minor diameter and on the flank standard nut system but with no clearance on the major diameter is indicated in this diagram. Have a look at the formulae associated with the dimensions indicated in both diagrams. The diagram figure 4 shows the profile for multiple start threads. PH indicates lead and P refers to pitch. Multiple start threads have the same profile as single start threads with lead pH equals pitch P. For the pitch P of multiple start threads, only the values permitted for the lead P of single start threads may be selected. However, the multiple of the pitch P of multiple start threads need not correspond to the value permitted for single start threads. Thread is a ridge of uniform cross-section which follows the path of a helix around the cylinder or cone, either externally or internally. Helix is a type of curve generated by a point which is moving at a uniform speed around the cylinder or cone and at the same time moves at a uniform speed parallel to the axis. Threads are used for fastening purposes. Example, bolts and nuts. Transmission of motion. Example, half nut with lead screw. Precision measuring instruments. Example, micrometer spindle. Load lifting purposes. Example, screw jack and elevating arm of radial drilling machines. Elements of thread means naming the parts and other terms systematically. The parts of a thread are major diameter, minor diameter, pitch diameter, pitch of the thread, crest, root, flank of the thread, thread angle, depth of thread, lead angle or helix angle, lead, hand, clearance and major diameter. Root or bottom is the bottom surface joining the two adjacent flanks of the thread. Flank or side is the side of a thread surface connecting the crest and the root. Crest or top is the top surface joining the two sides or flanks. P indicates pitch in millimeters or threads per inch. Beta refers to the profile angle. Phi refers to the helix angle of the thread. D is equal to the major diameter, external or internal. D1 is equal to the minor diameter, external or internal. D2 is equal to the pitch diameter, external or internal. Pitch diameter is the effective diameter of the screw thread, approximately halfway between the major and minor diameters. Helix angle is the geometrical shape of the screw thread. It is based on the pitch diameter of the thread and the pitch, that is, the distance from one point on a thread profile to the corresponding point on the next. The formula for calculation is shown here. This measurement can be represented by a triangle being unwound from the component. The same pitch on different diameters gives a different helix angle as shown. Let us see how to turn the component as per drawing and make buttress thread on the component. To do this, you need the raw material, cutting tool, 4-jaw chuck, buttress thread, measuring tool, undercut tool, threading tool, and drill chuck and drill bits. The job sequence is as follows. Check the raw material size. Hold the job in a 4-jaw chuck and screw it. Face one end and center drill the job. Reverse the job and face the other end to a length of 280 mm and center drill it. Hold the job in between center. Turn helix angle 30 mm to a maximum possible length. Chamfer the end 2 by 45 degrees. Reverse the job and turn the step helix angle 25 mm for 255 mm length. Turn the step helix angle 7 by 8 inches or 22.2 mm for a length of 215 mm. Turn the step helix angle 18 mm for 15 mm length. Set the undercut tool of 5 mm width and make undercutting to the given depth as per the drawing. Set the threading tool of 45 degrees and 90 degrees to the correct position. Set the machine to cut 9 TPI thread. Cut the 9 TPI buttress thread. Deburr the job and check the dimensions.
We have reached the end of this session on Make the Carpentry Vise Lead Screw. By now, you should be able to know the carpenter vise, explain the buttress form of thread, describe the screw thread, turn the component as per drawing, and make buttress thread on the component.
Today I will be discussing on CPgrams, which is Centralized Public Grievance Redress and Monitoring System developed by NIC for Department of Administrative Reform and Public Grievances. It is an online platform available to the citizen